on. So hello everybody, this is the next episode of our series of seminars from mathematical physics in Prague. And in this episode we will resume with the topic of Spyros. We'll somehow continue very likely on the topic he gave us last time. And today the title is algebraic, cubic and non-cubic operator time from. So looking forward to yours.
Thank you very much. So last time we discussed about Dirac operators in the supersetting for literature algebra. And before that, actually, we had organized an unofficial somehow talk about the Dirac operators, the standard one. I mean, for the standard case for Lie algebras and for symmetric pairs. So today I will be talking about the generalization of Dirac operators, always for the standard case, but in a broader somehow setting. So we will talk about cubic and hopefully about the non-cubic Dirac operators, and then probably in some next lecture I would like to talk about. I would like to study first of all, and then talk about Dirac operators, cubic Dirac operators in the supersetting. So this one it will be somehow the necessary context in the standard case that one has to know in order to proceed to the super case. So let me start with the denotation. So G will be, as always, semi-simple complex Lie algebra. So with T, we will denote a Cartan subalgebra of G. And with this bilinear form, we will denote the killing form of the symmetric, invariant, non-degenerate form, bilinear form defined on G. Okay, so let me start with the standard algebraic of Dirac operator. So the simplest context that we can consider is the following one: G is decomposed into K plus P, where K is the maximal compact subalgebra of G, and P is the orthogonal complement. So this is called the Cartan decomposition. And P is just the orthogonal complement of K with respect to the killing form. And in this case, of course, if you want, in the definition of the Cartan decomposition, we have that the restriction of the killing form on K is a non-degenerate. And this is why actually we have this orthogonal decomposition. And then we have the following composition. Then one can, of course, consider the Clifford algebra of P. The Clifford algebra of P acting the corresponding spin module. And then, so S is a module for this Clifford algebra, but on top of that, S can be equipped by the following composition map by a K representation structure. So the essential here is that S is at the same time a module for the Clifford algebra and a K representation. And then for every G module X, we define a Dirac operator to be the following linear operator acting on the tensor product X tensor S, and which is given by the following formula. Where Zi is an orthonormal basis of G. So here Zi acts on the first factor just by the G action, and here we have just a Clifford multiplication. So this is an element in the Clifford algebra acting on the spin module by this action. Yeah. And then this module here, this tensor product. So S has a K representation structure. So S is a K representation. X is a K representation as well by restriction. And this operator turns out to be K equivariant. So properties. So the first one, okay. So this operator is well defined in the sense that it does not depend on the choice of the basis. And the second property is what I just mentioned. So this operator is K equivariant. That means that the K action on this tensor product and our operator commute. And that means that, as a consequence, the kernel of this operator is a K representation. So it makes sense in representation theory to study this operator. So here probably for just a convention. There is a constant here. Just a convention. Okay, and the third property is the following one. The square of this operator gives a sort of a Laplacian, actually, an algebraic Laplacian. An algebraic Laplacian means a Casimir element. So it has the following form. The square of this operator has the following form. So omega g is the Casimir of G. So this guy acts just on the first factor, just on X. This omega k here is the Casimir element of the algebra k. And then delta is just the diagonal action on this tensor product. So omega k is the diagonal action. And then this is just a scalar. Rho stands for half the sum of the positive root of G, and rho k stands just for the half sum of the positive roots belonging to K. So this is just a scalar. And this property is very crucial, very important when we study Dirac operators for the following reason. Because, for example, consider that we have a GK model. So assume X is a GK module. A GK module means that X at the same time is a G representation, and it is a K representation. K is a maximal compact subgroup. If you want, K is the group which gives this Cartan decomposition. I mean, K, Gothic K, just the complexification of the algebra of this liquid. So we have two actions, one coming from the algebra G and one coming from the group K. These two actions, in some sense, they should be compatible. And moreover, X is decomposed into a direct sum of finite dimensional irreducible representations. So I repeat, X as K module is decomposed into a direct sum of finite dimensional irreducible representations, and then we collect all these finite dimensional representations of the same type all together, and we create these blocks which are called the isotypic components. So this K module here is just a direct sum of finite dimensional irreducible representations of the same type delta. And then, of course, if we tensorize X with S, which is a finite dimensional module, then we have again this kind of decomposition. And it turns out, one can very easily check that this square acts on every such isotypic component by some scalar. Why? Because, I mean, when X is irreducible. Why? Because the Casimir element acts on the first factor, by the infinitesimal character of X. The second guy here acts just by a scalar determined by this element here, and then we have just a scalar. So on every isotypic component, the action of this square is given by a scalar, determined by this delta. So this property is very crucial if we want to study these Dirac operators. Okay. And now we are going to talk about cubic Dirac operators. We would like to generalize this construction in a broader context, in a more general context. So again, we have G, a complex semi-simple algebra, but now instead of K, we consider a subalgebra H of G, such that we have two conditions. The first one is essential. So we assume that the restriction of the Killing form on H is non-degenerate. So this condition is essential if we want to define a Dirac operator. And then for the sake of simplicity, we assume that the complex rank of G and H, so actually H is reductive about. So we assume that the complex rank of G and H is the same. So in other words, T, this Cartan subalgebra or some Cartan subalgebra of G is contained in H. So H is a reductive subalgebra. And because we have this condition, we have a similar decomposition, which of course will not be the Cartan decomposition, but we will have an orthogonal decomposition of G. So then G is decomposed again into an orthogonal decomposition, where Q is of course the orthogonal complement of Q. Excuse me. Yeah. So Q is the orthogonal complement of H with respect to the Killing form. So you see that we have actually exactly the same setting, apart from the fact that instead of K we have a more general subalgebra H. And now, of course, we can define the Clifford algebra of Q, a spin module. For this Clifford algebra, we have again a composition map which equips S, which equips S with an H representation structure. So actually we have everything that we need in order to define a Dirac operator. Okay, and now the question is, define the Dirac operator for a G module X. So the first attempt, I mean very naively, one can say, okay, so far everything looks similar. So I will take again an orthonormal basis of Q, an orthonormal of Q, and we will I will use the same formula as before. I will define a Dirac operator to be given again by the same formula. So we have a sum. And let's call this operator D hat. So this operator again, it will be H equivariant. It will be well defined, but it will not satisfy the third property that we had before, the nice formula for the square. So if we define our operator using this formula, it will be much more difficult to study it because we don't have this nice formula. And I mean, almost every result that we have proved the algebraic Dirac operator is based on this nice formula from the square. So this is not a good definition, at least from the representation theory viewpoint, to define our Dirac operator. Okay. Second aspect. By Goette and Kostant. So Goette and Kostant suggested a modified operator so we use on the first part we have exactly the same formula. But we must consider a correction term here. So we have exactly the same form, the same sum, but here we have an extra term which acts only on the spin part of the tensor product, x tensor S, and it has a name. This element is called the cubic element of the Dirac operator, and it is given. I will not give the explicit formula. I want just to say that this element, this degree 3 element belonging to the Clifford algebra, is given as the image of this trilinear form. So here we have a trilinear form, alternating trilinear form, and using the Chevalier map, this element, this cubic element C, is just the image via the Chevalier map of this trilinear alternating form. And now with this definition, we have the nice formula for the square.
So the Chevalier goes into the Clifford algebra, or
Yes.
yeah.
From the exterior algebra to the Clifford algebra. Yes.
Take the orthonormal basis and replace our exterior multiplication.
Yeah. Exactly. Okay. And now with this new version of Dirac operator, let me say that in case that H is a symmetric subalgebra of G. That means that when H is the fixed point set of some involution, then in this case C is just a 0, so we don't have to consider this cubic term. So in our case, H will be non-symmetric. So this guy here will not be 0. And then we can again, as we did in the case of super algebras, or as we did for the standard setting in the first talk, we can define Dirac cohomology, which is the following question. Consider the kernel of the Dirac operator, the cubic Dirac operator, over this question. Now we have again a Vogan's conjecture. As we had before in the super case or in the standard case, which says that if X is irreducible, and the Dirac cohomology is non-trivial, then we know the infinitesimal character of X. Here we don't have GK module, we have somehow GH modules, if you want. And in some cases we know how to compute explicitly the Dirac cohomology. One of these cases is, for example, when the module is finite dimensional. We have an irreducible finite dimensional module. And we have a nice formula due to constant for this case.
I'm a bit lost. You start with, I'm a bit lost, sorry, if I may shortly interrupt, you start with an admissible GK module or GH module. Finally, to generate it over UG. X, yeah, sorry. If you could remind me the X.
In this case, or in the previous
In this,
case?
yes.
Yes, you have a G8 module if you want. I mean,
admissible not, it doesn't matter. Because character.
But I think that if a GK module is irreducible, probably it is automatic.
Irreducible. Aha, sorry. Okay. Yeah, okay. I'm sorry.
But in any case, admissibility
There should be two R's. I see. One R.
But in any case, they, at least for these results, admissibility is not very important. Okay, and now in the case, as I was saying, in some cases we can compute explicitly the Dirac cohomology. For example, when x is a finite dimensional irreducible module with highest weight lambda, this lambda here, then and always with the equal rank condition, then the Dirac cohomology is exactly the kernel of the operator, so we don't have to consider the quotient, just the kernel of the operator. And this kernel is decomposed into H irreducible, finite irreducible subrepresentations. Which are given by this direct sum. Where here f with f is just the irreducible, the finite dimensional irreducible representation of H corresponding to this highest weight of H. And here W1 is a subset of the valid group consisting of the elements which satisfy this property. So this is the set of positive roots for G. This is a set of positive roots for H, and we want this condition to be satisfied for the elements of W1. So in other words, we change the positive system of G, but we don't change the positive system of H. Okay, but now for some reasons coming from, I mean, I have a motivation from differential geometry. I don't know if I will have enough time to say something about this motivation, but we want to define and study the following family of bad Dirac operators. So we define the following one-parameter family of linear operators which are very similar to the Dirac operator. So for every t belonging to this interval, we define the following operator. So the first part is exactly the same. But here, instead of minus the cubic term, we have minus t times the cubic term. So before, for the cubic operator, there we have just a coefficient 1. Here we perturbate, if you want, somehow this cubic term. And of course, for t equal to 1, we have again the cubic Dirac operator that we defined before. So when t belongs to the open interval, we call these operators t cubic. T-cubic Dirac operators. In the special case where t equal to 1, we have exactly the cubic Dirac operator that we defined above. And when t belongs, when t takes the extremal values, so t is 0 or 2, then we will say that this d hat operator, let's say for example that t is equal to 0, we call this operator the non-cubic Dirac operator. So all these operators are well defined and age equivariant, but apart from this one, whenever gamma c is not 0, apart from this one, all the other operators do not satisfy the good property for this square. So they are somehow bad Dirac operators. But for some reason we want to study them. And it turns out that question. Now we describe the kernel group of neutrons. So in general, this question is very difficult because these operators can be very wide. But in the particular case where, so in the special case where x is again a finite dimensional, yet useful representation with highest weight lambda. So in this particular case, it turns out that all these operators have exactly the same kernel with the cubic Dirac operator. Whenever T belongs to the open interval. So even if I mean, although these operators are very bad, they turn out that it turns out that they have exactly the same kernel with the cubic Dirac operator. So in other words, we can compute explicitly their kernels. It will be given exactly by this formula. And for the proof of this theorem, which will be part of my thesis, I mean, the first step was the following observation. And this is how everything began. So the first step was the following observation. So the cubic term annihilates the kernel of the Dirac operator, the cubic Dirac operator. As the cubic operator plus some multiple of the cubic term. So in other words, if this guy here acts trivially on the kernel of this guy here, that means that the kernel of this guy here is included in the kernel of this guy here. And this property, I mean, this property here is not very difficult to be proved. Actually, what we have to consider is the following fact. Let's take again this nice formula for the cubic Dirac operator. And let's see which are the highest weight vectors which gives these representations here. So for example, for W1, this component here is given exactly by the highest weight of V lambda and the highest weight of the spin module. So for W1, for W equal to 1, the corresponding highest weight module of H is generated by the highest weight vector consisting of the highest weight of V lambda and the highest weight of the spin module. But then
Or it's sum, yeah?
excuse me?
It's sum? If that
No, tensor product.
Is that, yeah, tensor product.
But the operator has the following formula. And so let's say that this is the highest weight of V lambda, and this is the highest weight vector of V lambda, and this is the highest weight vector of the spin module. And so, according to this formula, this guy here belongs to the kernel of this guy here. So this operator annihilates this vector. On the other hand, this sum, these are root vectors belonging to Q. So this is a positive root vector, so it will annihilate this guy here. And this sum, for this sum, this guy belonging to the Clifford algebra will annihilate this guy here. So it gives 0, it gives 0, it gives 0. So at the end we have just this cubic term acting trivially on this guy's weight vector. But that was just one representation of them. For W being 1, what will happen with the others? But we can change the positive system of G without changing the positive system of H. So using the same argument, but with another positive system for G, we have exactly the same, exactly the same argument applies in all the cases. And so it turns out that this is true. And actually, as a consequence, the kernel of the cubic Dirac operator is included in the kernel of the T cubic Dirac operator for every T. So this is how we proved the first inclusion, which was the easiest one. And then for the second inclusion, I spent almost a year actually trying to prove the second inclusion. And finally it was something very elementary, but I mean, if I had known before this result coming from linear algebra, everything would have been much simpler. So for the second inclusion, for the other inclusion, we use the Weil's inequalities. So Weil's inequalities Weil's inequalities is the famous inequalities concerning the following question. So suppose that we have two matrices, two Hermitian matrices. So A and B are Hermitian operators acting on a finite dimensional space. So A and B are two matrices, Hermitian matrices. So they are diagonalizable. They have an eigenvalue, say lambda 1 of A is bigger than lambda 2A. So we arrange all these eigenvalues. And the same for B. So what can we say about the eigenvalues of the sum? So we have two matrices which do not commute, Hermitian matrices. What can we say about the eigenvalues of their sum? I mean, it is a very natural question, isn't it? Does anybody know anything about that apart from you?
It's related to this Horn conjecture.
Yes, exactly.
And that's related to supercapitalism in some sense.
Exactly. Exactly. So Weil's inequalities state that, I mean, we cannot hope that we will have explicitly the eigenvalues, but we have some inequalities. And say the following. So we have these inequalities. The ij minus 1 eigenvalue of A plus B is smaller or equal to the sum of these eigenvalues. And now we can calculate. Now we know which are the eigenvalues of this operator. We know which are the eigenvalues of this operator. And we want to calculate the eigenvalues of this operator. So actually, the eigenvalues corresponding to 0, the 0 eigenvalues, the 0 eigenspaces of this operator. And it turns out that, I mean, and then you should translate these inequalities in the Lie algebra language, and it turns out that the kernels are equal whenever t belongs to the open interval. And then when t belongs to takes the extremal values, then you should change somehow your method, and you obtain again some results which are more complicated to state. Okay, and all this actually, the motivation, I will not be very precise, but actually the motivation for the study of these operators comes from differential geometry, because there you have homogeneous spaces, and Slevarsky, Agricola, and probably some other authors consider the Dirac operators with Dirac operators coming from continuous families of connections, joining the canonical connection of the homogeneous space and the Lefschetz connection, and then they start these Dirac operators in this context. And it turns out that the algebraic analog somehow is this one. So by studying these operators, these bad operators, you can obtain some results for the Dirac operators. And I think I don't have a.
That looks a bit light, but wish.
Yeah, I mean, if I start, I will need I mean, I will have to define these geometric Dirac operators, so I will. I think I will stop here.
Thanks for the. Now, questions time.
The Vogan conjecture was proved by Panjic and Huang.
Yes.
Where was it?
American Journal of Mathematics.
2006.
When or where?
And
2006. Two, bro, I don't know.
Okay.
The beginning. And then probably they proved they proved Vogan's conjecture for GK models, and then Kostant with his Dirac operator generalized this result for the cubic operators. And since then, many other proofs for many different categories of models and pairs.
So these inequalities are like are they connected to permanence or to some to determinants formulas? These interlacing properties, or you ask whether we saw it once these inequalities, and I remember that I maybe saw it there. So
I mean, you have a determinant, and you want to estimate the determinant of the sum using. I don't know. No, I don't think so. But
either possibility is cyclic or is permanent with some adding units, cyclic units, and is permanent.
I don't know.
It appears also in Kasmuri algebras and tensor product is interlinked.
You mean these values and inequalities?
I forgot it.
But they are, as Ray said, they are related to Horn's conjecture, which Sugar says.
For this T-cubic guys, so suppose you have a corresponding cubic Dirac, you have characters that gives you homology. Does this character, this K-type, say you something about T-cubic guys? Because okay, they know that the kernel is the same, but this representative of this homology in this kernel.
I mean, if I understand correctly, you are asking if Vogan's conjecture gives you a hint for which components appear in the kernel.
Kind of.
No, because you don't have Vogan's conjecture.
Yeah, but I mean, you have the same kernel.
Yes.
So this guy lives inside.
Yes. Yes. I mean, at the end, it turns out that yes, okay, Vogan's conjecture remains true for this case, but I mean, you cannot go the other way around because you don't know that Vogan's conjecture holds.
So you cannot really determine which is how they lives in the kernel.
Yes. But this is actually a good method when you have a nice Dirac operator. I mean, you want to find the Dirac homology, you say, okay, Vogan's conjecture imposes some restrictions. I mean, what appears in the Dirac homology must have the same infinitesimal character with what I started with, actually. But not in this case, because we don't know.
So we spoke about the kernel. So what is naive question? What is the role of the base? Complicated question. What is the role of the image? What the images here actually in your talk? You spoke about kernels, right? What is the role of the image in the whole I know the role maybe, yeah. The role is
What I can say is that-
to make the motion exist.
Yes.
But
Yes.
what is
Then, for
Yeah,
example, I say that for the finite dimensional case, or more generally for a unitary case,
Mhm.
the image is just the orthogonal complement of the kernel.
kernel?
So in this case, first of all, the cohomology is just the kernel, and you can find the image, just the orthogonal
that's
complement of the kernel. But for the other cases, it's difficult.
Also, the self-adjointness made by error.
If D is not self-adjoint, the module that we started with is not unitary, then you cannot say anything, as far as I know.
Actually, to compute the character, the image would be maybe important in the infinite case. Infinite dimensional characters of infinite dimensional modules. But it is the same module. It's similar. Some.
Okay, any other question?
Maybe historical. I remember this Dirac operator, this parameter t, this non-cubic Dirac operator, was used by geometers who you mentioned, like Agricola
Yes.
and etc. They were already established, found by Kostant, or not?
No, I don't
No,
think
or
so.
these were by Narasimhan, or
As far as I know, Kostant introduced his Dirac operator, and then Agricola defined the continuous family of connections, and somehow this family gives, contains Kostant's operator, but for a particular value.
they interpret these Chevalier things as torsion.
Yes, exactly.
Terms.
Yes, and this cubic term corresponds to the torsion of, something like that.
But this trick this T, if you could attribute this, well, I can find it by myself. This trick, duplicating this parameter T is maybe came later than Kostant.
I think so. The connections that Ilka considered, as far as I remember, because just yesterday I had a look, it was something like a connection with parameter t equals to the canonical connection plus t times the bracket restricted to M, something like that.
Yeah, so you think Ilka will establish that?
Yes. But then Slebartis had already studied some similar questions.
That is a couple weeks ago.
Yes.
Would have one terminological question, maybe. Non-cubic operator means that you pose t equals to 0, or anything outside the interval 0 to.
The non-cubic, we call the operators with when t equals either 0 or 2. Because for these two operators, for the extremal values, this result is not true. The kernels do not coincide. You have something more actually for the non-cubic. So this is why we call them, when t belongs to the open interval, so the theorem is true, we call them t-cubic because they are very similar to the cubic one. Their behavior is very similar to the cubic one. And for the extremal values, we call them non-cubic because they do not behave the same way.
and maybe one related. You claim that the third condition for your Dirac operator is crucial for further proving some statement. Which one, for instance?
For everything, actually.
Okay.
I mean, all the results that I've read about concerning Dirac operators at some point use this nice property for this square.
I see. So there's just a
Small comment.
Yeah.
It's originally also observed by Kostant that for the mathematical physics part of the audience, that these cubic guys are somehow related to the corresponding 2D Toller chains. So I will just refer to his thing.
Translation is
Very unexpected.
This is the article that he established these operators. I mean, the emergence of oil is okay. I will have a look at it. Is the camera off?
Yes.
I want to say something about the Kostant's paper. I mean, I think that they are not very well written. I hope.
Maybe I should the camera. So thanks for the.
Yeah, I mean, they are very